Welcome to these lectures on linear algebra. Recall that last time we have been studying vector spaces and subspaces and so on, and last time we have proved existence of a basis of a vector space under the assumption that it has a finite generating system. Today I want to prove this theorem for arbitrary vector spaces. So, today's lecture we will prove the existence of, so let V be an arbitrary vector space. K vector space, and we proved this lecture we will prove a very important theorem that V has a basis. Note that we have proved this theorem under the assumption that V has a finite system of generators. In this case, I will also keep saying shortly V is finite. Does not mean that V as a set is finite, but it has a finite generating system. Now we want to do it arbitrary. So, and then in the second part we will compare the size of the basis, size of any two bases. For that we will need a concept of cardinality, etc. This I will recall when we will need it. So, I am going to improve the lemmas which we have proved under the assumption that V is finite. So, first of this is, so let us call this as a lemma. This says the following. Let I will not keep saying let V be an arbitrary vector space over a field K, that is a standing assumption. So, let xi I in I be a family of vectors in V. Assume that, suppose that xi in I is linearly independent. Over K, and x is another vector in V. Then this family xi I in I along with x is linearly dependent if and only if the vector x belong to the subspace generated by x's. Recall that this is our notation for the subspace generated by the family xi, and by definition it is the smallest subspace which contain all the vectors x's, and elements of this subspace are precisely the finite linear combinations of exercise. So, let us prove this proof. Proof is similar to the case when V is finite, but let us write down the proof for self-containedness. So, first I am proving this. I am proving this. That means I am proving the fact that if x belong to, so assume that x belong to this subspace. Then what do I want to do? I want to produce a non-trivial relation among the family xi along with x. So, this means x belong to this means x is a linear combination ai xi I in I, where the coefficient tuple ai belongs to k round bracket I. And again recall that k round bracket I means only finitely many components in the tuple ai are non-zero. Okay. Then you keep shift the everybody to the other side and equate to 0. So, that means 1 times x plus summation I in I minus ai xi, this is 0. This is a non-trivial dependence relation among the family xi along with x. Non-trivial because this coefficient of 1 is coefficient of x is 1, which is not 0. So, we therefore it proves that this family, this extended family, when I join x to the family xi, this is linearly dependent. Now, the other way is this. Now, we are assuming the family xi, this family is linearly dependent. So, we are assume xi I in I union x is linearly dependent over k, always over k. So, that means, that is we have a non-trivial linear dependence relation. That means we have a relation like this, ai xi plus some ax is 0 I in I, and as usual this coefficient tuple ai, this tuple is in k round bracket I. So, note that because this family xi is linearly independent, this a has to be non-zero. So, first note that a has to be non-zero. See, a is also in k, and because this is non-trivial dependence relation, not all ai I in I and a are 0. At least one of them is non-zero, but I claim that non-zero guy, this a must be non-zero, because if a were 0, then we will get summation ai xi is 0, and because xi are linearly independent, then ai will be 0, then all these will be 0, but that is not true. So, ai is non-zero. So, a inverse makes sense in k because k is a field. And now rewrite this equation by shifting x to the other side, multiplying by inverse. So, you will get x equal to minus a inverse ai xi I in I, and by using usual vector space rules we get this is minus a inverse ai xi I in I. So, this is this right hand side clearly belongs to the subspace generated by x's. So that is what we wanted to prove. If this extended family is linearly dependent, then X must be in the subspace generated by Xi. That was to be proved. So that proves the lemma. Next proposition is similar to what I have proved in finite case. So that is a proposition. So let Xi I in I be a family of vectors in V, and this proposition tells the equivalent conditions. How does one check this is a basis? So then the following are equivalent. Okay. 1 Xi I in I is a K basis of V. This is what we are interested in, finding the basis. 2 Xi I in I is a maximal, I will just put this in quotes in a minute, maximal K linearly independent family in V. 3 Xi I in I is a minimal generating system for V. So now let me just repeat the maximal and minimum, because we are not in a finite case. So everything is happening in the power set of, so note that, so before I indicate the proof, recall or note that we are power set of V with the natural inclusion. This is an ordered set with this order natural inclusion. And ordered set means three things. Order is in relation. So order on a set is a relation which satisfies three properties: reflexive, transitive, and antisymmetry. A model prototype example is a set of natural numbers with the usual less equal to. This is a prototype example. Or Z with integers with the usual less equal to. These are prototype. Or another example is a power set of a set with the inclusion. Okay, now when one says maximal, that means one says somebody is a maximal element in an ordered set if no proper bigger set or nobody maximal than that is there. So let me write formally. An element X in the order set X less equal to is called maximal element in X if there is nobody bigger equal to X. So if there is no y in x with x less equal to y and x is not y. So, such a element is called a maximal element. Similarly, analogously we can define minimal element. And an ordered set can have more than one maximal element. When there is only one maximal element, that is called a maximum, and similarly for minimal and so on. So, this second condition says that this family is linearly independent and no strictly bigger family than this is linearly independent. So, that means if I add any extra element to this family, then it becomes linearly dependent. Similarly, the 3, that it is a minimal generating system, means it is a generating system, and if I remove any element from that generating system, it cannot be a generating system. So, now let us quickly prove it. It is very simple. So, proof. For example, 1 if and only if 2 actually is proved in the earlier lemma. Is proved in earlier lemma, that is precisely earlier lemma. Similarly, 1 implies 3. This is also immediate from earlier lemma. So, only to prove therefore 3 implies 1. This is the only implication we need to prove. And what is 3? 3 is given. So, suppose this xi is a minimal generating system. For V, and we need to prove 1, that is to prove that it is a basis xi I in I is a k basis of V. We need therefore to prove that this family is linearly independent, because linearly independent generating systems are precisely called a basis. So, to prove that this family xi I in I is k linearly independent. So, that means we suppose there is a dependence relation and prove that each coefficient is 0. So, suppose we have a relation, linear relation like this, ai xi equal to 0, I in I, and the tuple I tuple ai should have only finitely many non-zero components, and we need to prove that all ai's are 0. We need to prove this all. So, suppose some ai's were non-zero, if let us say a I naught is non-zero for some I naught, then we need to get a contradiction. Then again rewrite this dependence relation by keeping this term corresponding to I naught on one side and shift to remaining terms to the other side. And because this ai naught is non-zero, ai naught inverse exists and it is an element in K. So, I rewrite and multiply that equation by ai naught inverse. So, we will get equation xi naught on one side equal to minus ai naught inverse summation ai xi I in now I and remove I naught from there. because I naught term I have brought it this side and multiplied by that, but that as usual vector space rule, this will tell you minus ai naught inverse ai xi I in I and not I naught, but this is a subspace generated by the remaining vectors other than I naught. This is k xi I in I and I is not equal to I naught. So, this is a contradiction to the fact that it is a minimal generating system, because this means we can drop out xi naught. That is not possible because assumption 3 says it is a minimal generating system. So, that proves 3 implies 1. All right. So, we have proved the lemmas. Now, I will first I will state a theorem, and maybe I will need to recall something again from the ordered sets, and also I will, in this lecture we will need to use Zorn's lemma, which is very important lemma, which is also equivalent to axiom of choice and so many other statements in set theory. But Zorn's lemma is a statement which ensures the existence of extremal elements in an ordered set, and this I will elaborate on this when we just before we prove the theorem. Okay, so the main theorem I want to prove is the following, and we will deduce our theorem from this theorem. So, this theorem says, so let xi I in I be a generating system. For V, and we want the process to either to minimize it or to maximize the linearly independent sets. By earlier proposition, we know that a minimal generating system is a basis or a maximal linearly independent set is a basis. So, we have to find a method so that either we can minimize the generating system or maximize the linearly independent sets. So, suppose that, and we can always choose a generating system for any vector space, because worst come to worst we can take all vectors in that system. That is clearly a generating system, but it may be too big. So, we want to have some process. So, suppose that subfamily of this xj, j in j, where j is a subset of I. Such a thing is called a subfamily, because we are taking the few elements from that given family. Suppose that this is k linearly independent. Subfamily. This is also again possible. Worst come to worst, we can take empty set. J equal to empty set is, empty family is always linearly independent. Okay, then what is the assertion? Then we can enlarge the J. There exists J tilde, a subset of I, with it should contain this given J, and the subfamily indexed by J tilde is K linearly independent. No, not only K linearly independent, but maximal is a K basis. of V. So, in particular V as a basis. So, to prove this theorem, we need some mechanism to enlarge this family to a maximum possible. So, that means we are looking for a maximal elements. So, to prove this theorem, we need to use John's lemma. John's lemma, as I said, John's lemma is John's lemma gives a condition on an ordered set so that it has maximal elements. So, let me state John's lemma first. So, let x less equal to this be an ordered set. We need some assumption to put on this ordered set so that we can infer the maximal elements. Obviously, you see the standard model what we know, n less equal to, as you know, this does not have maximal elements. So, arbitrary ordered set will not work in general. So, I will write the term and then define the term. So, suppose that x less equal to is inductively ordered. I will define this term inductively. If you have this assumption, then we can say that then x has maximal elements. Now, let us recall what is inductively ordered. So, recall that x less equal to is called inductively ordered if every chain in X has an upper bound. So, again let us recall what is the chain in an ordered set. Chain in an ordered set is precisely a total ordered subset, totally ordered subset of X is called a chain. Or typically, for example, if you take this n less equal to, this is already chain, whole X is a chain in this case, but finite subsets are also chain and so on. Finite subsets of any ordered set is it will have obviously a maximal element because you can compare. It may not be chain, but the assertion that it has a maximal element can be easily checked for a finite ordered set. Okay, what is an upper bound for a chain? So, in general, if you have a subset y of x, upper bound for x, upper bound for y in x is an element x which may or may not be in y with the property that y should be less equal to x for all y in y. Then such a thing is called an upper bound for y in x. So, now I guess all the terms are clear in this, and we will continue the proof of the theorem by using the John's lemma in the next half. Thank you.